Okay, is it visible now?
Yes,
Okay, cool.
you can go ahead and start.
Okay, okay, let me start.
Please do.
Hello, everyone. Good afternoon, good evening, or good morning, wherever you are. My name is Jobin, Senior Support Engineer working for Percona. Today's my topic is Postgres WAL commit synchronization and optimization opportunities. So this is going to be a short presentation. I'll be going through the slides in a rapid phase because we have less time. So today's agenda is what is WAL record, what are the WAL records, and what need to be considered for synchronization, and what is important from host IO subsystem, and the parameter tunings, and different levels of tuning, instance level, database level, user level, session level, and even at the transaction level. And we are going to discuss how it impacts performance and some basic checks on that. And then we are going to discuss WAL propagation to standby. Uh, After that, there is synchronization, some synchronous standby discussions. And what happens in the synchronous standby? The different stages like WAL write, flush, and replay stages, which we are going to discuss. So this is the agenda for today. So straight away to the WAL. So this is very basic. What is WAL? Because every new user asks this question. WAL is nothing but a journal of changes or ledger of changes. Everything happens in the database will be recorded there first as a sequential steps of changes. Um, uh, the commonly asked question is why we need to do this. First writing into a redo and then the WAL and then to data files. There are two things. One is it speeds up the transaction. Instead of going and writing n number of places in a transaction, there will be a lot of changes, say updation to multiple tables or multiple indexes. There are scattered along the database. Instead of doing all those things, the transaction can just insert the WAL records and proceed with the transaction. There is a that way it speeds up the transaction. And moreover, the WAL writing is unavoidable for transaction processing, not just speeding up, because without WAL, we don't have a record whether the transaction is committed or not. If the database is going and changing all the blocks across the tables, we don't have any way to know whether the transaction is committed or not. This serves the durability purpose of the durability requirement of the database. So in nutshell, WAL is the metadata to reconstruct the changed data in the database. And why WAL? Okay, we discussed about the crash recovery because we need to know what is committed and not committed. This is a very basic requirement because database should serve the asset rules. The durability is a minimum requirement, and instance crash recovery requires the WAL to understand the what is committed or not. And the second thing is restore from hot backup. This is again not that important as crash recovery, but in a production system, we may have to recover from a hot standby, sorry, hot backup, sorry, and that is can be served from using the WAL records, records. When the data, what is hot backup means is when the database is live, that time it can take the backup. Means the changes are happening throughout the database. Then applying the WAL will get the database up to certain point in time. So this is again a very important requirement from the database perspective. The third one is about the high availability. The WAL records can be replayed on the standby side to get the database in sync with the primary. So if the WAL records can serve as a high availability mechanism. So this is the third point, which is lesser important. And the fourth requirement is the logical replication. The logical changes happening in the tables may have to be streamed to some other system, maybe some even another database system like Mongo or somewhere. So we need to understand we need to have a provision to understand what are the changes, which tables are getting updated with what value. All those things will get recorded into WAL, and these require additional information. The table or the column which is getting changed. So additional WAL logging is required. So if you look at 1, 2, 3, and 4, we can see that the one is the first and the most important requirement, and the fourth is the last requirement, and requires the fourth requires more WAL logging, more information to be logged. So Postgres provides a parameter called WAL level to determine how much of WAL logging need to be happening. For instance recovery, we just need the minimal level of WAL logging. For restoring from hot backup and for standby, we require some more WAL logging. For logical replication, it requires more logging. Okay, and the basics are over. So coming to the WAL generation, this is what happens inside the Postgres. Every Postgres backend will be generating the WAL records. Say every user process will be spawning a server-side process, session process, and every transaction happening in that session will be recorded to the WAL. And like Postgres multi-user environment, there will be concurrent transactions happening. So all those things will be added to the WAL records, set of WAL records in the WAL buffer concurrently. And we need to understand this is a shared memory area. The WAL buffer is a shared memory area where all the backend will be updating the WAL records. And the WAL buffer size is auto tuned for the newer versions of Postgres. It is 3% of the shared buffer, but it is not part of shared buffer. The actual Postgres shared buffers, it's outside the shared buffers, and it is capped to 16 MB size. And this is the internal code for the calculation. And these buffers will be flushed as part of every commits. So if there is 10 commits happening, the last commit can cater to all the previous. It can flush out all the previous changes in the WAL buffer. So regarding the size of the WAL buffer, the 16 MB is the best for most of the users. But if there is an extreme busy system with a large number of CPU cores, I mean, the effective concurrency is, if it is too high, increasing to some 64 MB or 128 MB is found to help. Sometimes a few users reported that it's even doubled the performance. So, but that's for extreme busy system where the transactions are too high. Okay, and within the session, this is what happens. So first, the Postgres changes the shared buffers, that is buffer cache where the pages are stored. And as part of the transaction processing, it calls a xlog insert function within, and it inserts the WAL records into the shared buffers. And for supporting the concurrency, we have a very fixed number of logs, because the logs are required to reserve the space for the WAL records. So default is 8. This is an internal constant, which can be changed at the compile time. It's not dynamic. And this log is a structure that holds information about the progress also. And the WAL insertion is a two-step process. This is what, as an end user, we should be remembering. It reserves the amount of space in the WAL, and the space will be reserved for a process, and then the process can copy the records into the reserve space. So reserve and insert the data into that. Yeah, this is what happens in every session. And regarding the WAL writing, it invokes a internal function, p write, which actually calls the system call write. Uh, but this write system call is not guaranteeing the flush. So there'll be additional call for fsync later whenever a commit happens. And this is another point. The WAL segment files are 16 MB size, so it will be fsynced after each segment file is filled. So the fsync happens now and then. And this is one of the most frequently asked questions by users. So which process writes the WAL? Okay, as we discussed, the WAL buffer is a shared memory area. So, and each individual process is responsible for flushing it out. So each individual backends will be writing the vals, and there is additional val writer. But this val writer is an additional feature which periodically wakes up and it clears up the val buffer. Because there could be that lengthy transaction which is never committed. So this val writer is a supplementary process, but it's a mandatory. And okay, now we have the val records. Now we have the WAL records in the system, durable, and we need to have backups. So this WAL archives cater to this requirement. So vals can be archived. We can turn it on for a production system. And the other values like true, one, and s are undocumented. But for the presentation purpose, I mentioned here because the code supports those values as well. And from Postgres 9.5 onwards, we can have archive mode always, which means the vals can be archived from from the standby side. So the vals which are archived cater to the backup requirement. So it's additional recovery point. This next slide is for the DBAs. How do we monitor the val generations and its progress? So Postgres has the wait events. The wait event lists are increasing version after version. So these are the two major wait events related to the val generation, which we can monitor. One is the val buffer mapping, which waits for the replacement of page in the val buffers. So if there is a contention, this wait event will be more. How much the process will be waiting for writing into the val buffer. And another is val write. The val write basically waiting for the blocks to be returned, the buffers to be returned to disk. So since the generally the IO will be the bottleneck, we tend to see this more val write related wait events more in a busy system. But this is the way DBA can monitor. And okay, now coming to the flush. When the flush, what are the conditions the flush happens? We saw that every commit requires the flushing of the writes. On commit, definitely it need to be flush. And when there is a val segment switch, again, the flush need to be happened. And if there is a checkpoint, that also triggers a flush. And there are many more cases where the flush will be happening. So that which we need not worry now because the presentation is about the basics. Okay, so now let's look at the synchronization, how the WAL records are. So we discussed the WAL records are first inserted into buffers, then it is returned to the OS, and finally it is flushed. So in normal synchronization, which is we call local synchronization, um, which will guarantee the durability because the data is already flushed to disk. But Postgres, in Postgres, we can even select for a asynchronous commit, which means even before the flush happens, we have a facility to acknowledge back to the client. Say if I am doing a bulk data loading, which I can redo, I don't care about losing some of the information, I can redo that. Then I can opt for asynchronous commit. I can turn the synchronous commit off, and it will speed up the entire process. So, which is very useful for bulk migrations and data loading and things like that. So, the client will get immediate commit acknowledgement. But in every 200 milliseconds, definitely it will be flush to disk. So yeah, the window is around 200 to 400 milliseconds, which can be adjusted. Yeah. And now some key points which generally people miss about the synchronous standby, synchronization with standbys. The primary database defines which standby you wish to wait for. So primary standby committed a WAL record and handed over the WAL records to standby. Should I wait for the standby to acknowledge back whether it is reached there? So it's the duty of the primary to wait for the commit synchronization. And at the standby side, it is completely unaware about the durability requirement, whether somebody is waiting for, it don't know. So this architecture reduces the requirement to ship the state information from the primary to standby. Okay, and if there is a synchronous standby, the primary has option to wait for write, flush, or apply. These are the different stages happening in the standby side as well. So should I wait for a write to the standby side OS, or flush to its disk, or apply the changes back to its memory? So there are three stages. I will be going to see the in detail. And the primary will be maintaining an internal ordered queue of waiting backends. So whenever there is a acknowledgement back from the standby side, it can release all the standby. So all the waiters can be released at a time whenever. So the effective communication requirements also will be less by this bulk releases by the acknowledgement. Okay, if you look at the history, Postgres 9.5 had only one synchronous standby feature. The features were very limited. But in Postgres 9.6, we have what you call priority-based multiple synchronous standbys. So we can say first three of say standby 1, 2, 3, or 4. So the first in the list will be the synchronous standbys, and the primary will be waiting for the acknowledgement back. And in Postgres 10, we have the quorum-based synchronous standbys, where we can specify any of the standbys. So if we get acknowledgement from any of the standbys, any of the three standbys in the list, we can proceed. We can assume that the transaction is committed. So in Postgres, this is a parameter to specify the standby names, and the standby names is the application name of the standby. So which is because the standby will be connecting to the primary to do the replication. Okay. And coming to the synchronous standby levels, the remote write. Remote write means the WAL records are returned to remote standby, but not flushed. Okay, this is the point. And it will be waiting for in every case, it will be waiting for this acknowledgement back. When set to remote write, the commits will be waiting for reply from the current synchronous standbys. Indicating that they have received the commit records on the of the transaction and return out to the operating system, but not flushed, not at flushed. So this is what happens in diagram. The WAL records are inserted, and it goes to the local disk, and there is a WAL center process on this local Postgres, the primary side, and there is a WAL receiver on the standby side, and it writes to the OS. Then it can acknowledge back the primary that okay, it's returned to the OS. So the standby the primary can proceed with the acknowledgement, and we can go for the next level of durability by selecting a remote flush. So where the acknowledgement will be from the standby will be coming only after the flush to its disk. Uh, so once it is flushed, the acknowledgement will be there, and the primary can acknowledge back to its client. And the next level of um, synchronization is remote apply. This may be useful if there are concurrent sessions connecting to standby for read query, select queries. So it need to know exactly that the same isolation consistency rules. So once it is committed here and it is applied to standby, so we have pretty much same information here and here, then the primary that the transaction can be acknowledged from here. So we can be sure that the queries on this side will be seeing the same information. It's a pretty much perfect sync. So the coming to the IO recommendations, the WAL, as we discussed earlier, WAL is the main point where the transaction will be recording its statements. So the speed at which the WAL can be written determines the speed of the transaction. So low latency dedicated drives are recommended. And we found that reducing the checkpoint frequency also helps in reducing the amount of vals need to be propagated, because after the checkpoint there'll be a full page writes. Full page writes, the entire page of the Postgres will be written to the val. And these are some other optimizations which we can do for compressing the val. Say if you enable this parameter val compression on, the full pages will be compressed before writing to disk. And we have an option to compress vals before archiving, which can reduce the overall network bandwidth. And we have a Percona blog post about the same. And basically, this will be done by the backup tools or any of the Unix utilities, because the Postgres has the feature to include custom commands into the archive process. And regarding the commit synchronization, we have at a transaction level, in a transaction block, we can set the, we can even say commit synchronization is off. As we can see, the commit is off. And once the transaction ends, it will be back to the previous state, whatever it may be. And we can select the commit synchronization levels even at the session level by setting at the session level or during the connection time. So the session which will be created will have the in this case, synchronous commit will be off. And these are the other levels of some commit synchronization. At user level, we can specify, or at database level, we can specify, or at entire instance level, which generally we don't want to do. And if we are doing it at entire system level, we can just signal the Postgres to reload the new setting. And this is what happens if the val need to be propagated over a network. If the network is fast enough, we can see that the current val generation is pretty much what is sent to the standby. The standby side disk may be the bottleneck. It can be, but if we are seeing there is not much gap between the current val of the primary and what is sent to the standby, we can be sure that there is a very good network. And in a slow network, we may start seeing this: what is the current val generated at the primary side and what is sent. There could be some gap. And this is some basic benchmarks. I'm not keeping the TPS values here because it's relative. This is for just understanding the overhead. The values may differ from system to system. If commit synchronization is off, it will be extreme fast. It can acknowledge the client straight away. But if need to be flushed, this is the default, it need to be flushed to disk to acknowledge back. The disk will be the bottleneck. So there'll be a big drop in performance. And if need to be returned to a remote machine or a fast network, there'll be again slight decrease. And if there is extreme high delay in writing to a remote machine, say 200 milliseconds, the overall TPS drops like with a huge margin. And this 200 milliseconds is a wide area network from different data centers and all, but this won't happen in a normal case. And this is within the data center, 20 milliseconds or less than that, what we should expect. So still there will be a penalty, but depends on the network speed, the penalty may differ. And this is remote write, this is a remote flush, and this is apply. So we can see a slight decrease. Yeah, this is the price which we pay for the higher durability requirement. And this is another result which may be interesting, because very often I get the question, okay, if my local disk is the WAL is a bottleneck, can I hand over the WAL records to a remote standby, and can it be speeding up? The answer is no, because as we see, if it is it's a local high speed SSD value, the speed will be very high. But if you have a very slow WAL IO system, the performance decreases. To simulate the slow disk, I created a disk on the NFS, so that we can see the performance difference. And NFS with bigger latency, we can see that it further decreases. So this is our these are local synchronization. Then I introduced with the synchronous standby. So this will be a remote flush. The difference between these two are very negligible. So we can see that still the local disk is a requirement for even just handing over the records to remote standby won't be sufficient enough. Okay, and the same thing. If the local disk is a bottleneck, the same reflects in the remote write or flash or what. Yeah, yeah. The moment we have a faster disk, we have a better throughput. So in this case, we are clearly seeing that if we have a WAL mount point which is slow, that becomes the bottleneck in the entire performance. So with that, I'm pretty much done. I hope I could able to cover some of the basics about the synchronization. Yeah. Thank you. Any questions?
Yeah, thank you so much, Jobin, for the wonderful talk. So we have some questions for you.
Okay.
So you spoke about synchronization at different levels of scope. Is there any disadvantages of selecting different scopes? Why don't we see it so commonly?
Yeah, that's a very good question. I could not cover that part of this. When we do synchronization at different levels, for example, at the transaction level, we are within the transaction we are setting the synchronization. This requires the application to be modified. So the application session, within the transaction, we need to have this opt-in for a particular level, synchronization level. So generally, when we code, we may not be seeing this kind of injection into the code to opt in and opt out for a particular synchronization. This requires engineering for the Postgres at the design time itself. That's a major bottleneck. But if we are designing a system for Postgres, this can be incorporated for the right selection of synchronization. And in many places, we see this kind of things. Say here, the connection string is modified to have synchronous commit off. But in general, we see same connection string will be reused across applications, and there won't be modularity. All these things become a major bottleneck in applying synchronization at a different scope. Yeah, so basically we need to engineer for Postgres, that is to get the maximum out of maximum performance out of Postgres. Yeah,
Yeah, thank you. Thank you so much for the wonderful talk. Okay.
thank you.
Okay, so yeah, so next speaker is in the queue. Let me check who is in this. Okay.
Hi there.
Hey, how are you?
Nice. Thank you.
Yeah. Hi, Valerie. So next speaker is like Valery Kravchuk, and he is a principal support engineer in MariaDB Corporation.